error correction in the near future. Near future, maybe next 10, 20 years. Because ultimately, that's why we have developed the theory of quantum error correction, so that we could protect our qubits better from noise and decoherence. So in my first lecture, I'll discuss stabilizer codes and why are these codes that we study a lot because of their simplicity, basically. I will, in the second lecture, this is only a rough outline. The second lecture, I'll go a little bit beyond that. And I want to discuss some interesting codes that you may be less familiar with if you've already heard something about quantum error correction. Namely, encoding qubits in bosonic modes. And I think that's quite physically interesting. And I want to say a few things about how to do computation using error correction. And the last lecture, or part of the last lecture, because I may go slower than I want for the first two lectures, I will discuss how to do quantum error correction with the surface code and how to realize certain logical gates. I have a review on the archive from last year. Now I can say that. And so I will roughly follow this review. So if you want to read more, you can check it out and download it. There are also two exercises that if you have the solutions, you can discuss with me. And these exercises pertain more to lectures 2 and 3. Okay, so let's get started. Well, so what is a code is the most basic question. Now, simply, it's a specification of a subspace. Yeah? In some larger Hilbert space of many qubits. And just for some notation that we like to use in quantum error correction is that if we specify such a subspace, let's say it's a two-dimensional subspace, we want to discuss certain states, certain orthogonal states, the bases in this space, say spanned by two vectors, which I call a logical 0 and logical 1, two orthogonal vectors. Yeah? And once I specify these logical states, I can discuss operations, logical operators, which also are denoted with this bar, which map these states onto each other. Yeah? So the logical x, well, okay, so logical z acts like a Pauli z operator. Maybe in quantum error correction, you've probably seen this. It's common to denote the this one doesn't work. The three Pauli matrices are usually denoted that way. For notational simplicity. So I can discuss operators that act like are a representation of the Pauli z and the Pauli x, and of course the Pauli y. And they should satisfy the same properties that the Pauli z and x obey usually. Yeah? So they're anti-commuting, the same algebra, they realize the same algebra. So, of course, that's all well and done. That is what I define a code. It's very simple, just some subspace. Could also be a three-dimensional subspace or something. But then, if this is a subspace in an n-qubit space, its specification may be very cumbersome. For example, if I had to write down what these vectors look like. Because in general, they're highly entangled states of n qubits. And so this is where the formalism stabilizer code is very useful, because this specification is very simple for stabilizer codes. Because in fact, for stabilizer codes, we do not write down these code words, but we write down the operators that have these code words as +1 eigenvectors. Okay, so there are qubit stabilizer codes. There are also qdit stabilizer codes. And we'll also see in the second lecture that there are stabilizer codes which relate to infinite dimensional spaces, like a bosonic Hilbert space. But let's keep it simple just to get the basic ideas across. We talk about qubit stabilizer codes. Now, we can construct a group the Pauli group, which is this blue oval. And that Pauli group we're working on with n qubits. It's just a group of products of Pauli operators, including plus or minus the I times the identity in order to make it a group. Okay, so now we can take an abelian subgroup. That's this red thing. And let's call that S. That's the stabilizer. And this abelian subgroup is generated by a few elements in this Pauli group. Now, an example, and I denote, so the generator, so if I have a stabilizer that is generated by these two elements, I denote it with these brackets. So you may see this notation again. So I can look at this, this group, for example. And we also need to, we ask actually that minus identity is not, I don't put it, minus identity is not in S. That's the condition on the stabilizer group, and there is a reason why this is the case. So now, what is the code space? What is that subspace? How can I define that now? It is the +1 eigenspace of the group S. So this definition is like this. C are all the vectors, n qubit vectors, such that for all elements in S, S on this vector gives back itself. That is one choice of the code space. There are other eigenspaces where these eigenvalues are not +1 but can be +1 or -1. Now, a few small comments. Why +1, -1? This is, and these comments pertain to the simplicity of this structure with these Paulis. Paulis either commute or anti-commute. Makes life very simple. And their eigenvectors, eigenvalues are either +1 or -1. No? So, okay, so let's take an example of where I take this group. And so what are the vectors that are stabilized by these group elements? Now, for example, if I only look at this element, this vector 0, 0, or that vector 1, 1 are +1 eigenvectors, right? But I also need to be a +1 eigenvector of x1, x2. And so therefore I need to take a linear combination like this one, which is a +1 eigenvector of that state. So in this case, when I take this abelian group, the code space is one-dimensional. It's just one vector. I will, let me see, let me do this now. Maybe you write it down now. So I want another very simple example of a code. Is the one on 4 qubits where S is x1, x2, x3, x4, z1, z2, z3, z4. Is the notation clear for everyone? Like, this is important to, it's not very hard. Okay, so I'll come to that in a moment. Now, okay, so a few more things about this structure. One can view, and this is just maybe if I've been talking to a group of experimentalists to convince them of the simplicity of this structure, that one can view the generators of S, which of course are not unique. I can write all kinds of generators down, but I could view the generators of S, they can be viewed as parity checks. So if you're familiar with classical codes, parity check codes, where you have an n-bit code word, which has to obey certain parity checks on subsets of bits have to come out to be 1, and that defines the code words. These codes are quantum generalization thereof, in the sense that we're not looking at the usual parity checks. So this is checking whether the parity of those two bits is the same, or the parity is 1. but we're also checking the parity in a different basis. So that's quantum, that's the deviation from classical codes. Okay, so we can view these as parity checks. The eigenvalues of these elements in the Pauli group are always plus or minus 1. Now, of course, it would be nice to have a simple criterion to determine the dimension of the code. Yeah? So if I give you a bunch of parity checks and I say these are my generators of my stabilizer group, and I ask you what is the dimension of the space that's stabilized by this group, what is the answer? Now, that is nice about stabilizer codes, that this is a very direct answer to this. If I have k linearly independent checks on n qubits, linearly independence means that if I take, products of these, I don't get another element of these that in this generating set. With k linearly independent checks on n qubits, the subspace is 2 to the n minus k dimensional, encoding n minus k qubits. So the subspace always has this even dimension, so it always encodes a certain number of qubits. This for more general codes is not necessarily true. The subspace can be 5-dimensional or something. Now, the way to understand this is very simple, is that if you look at one of these elements here, I said they always have eigenvalue +1 or -1. So if I look at this, well, now maybe I have a check on, n qubits space. And half of that space, the vectors will have +1 eigenvalue, half of them have -1 eigenvalue. So if I say I'm looking only at the +1 eigenvalue space, I cut the space in half. So with one check, I get, instead of a 2 to the n dimensional space, I get a 2 to the n minus 1 dimensional space. And the next check, again, cuts the remaining space in half, because it's linearly independent. And I have a 2 to the n minus 2 dimensional space. So that's how this expression comes about. Now, then you can check for this code. So maybe somebody can answer this. Not somebody who is an expert. What is the, so here I have 4 qubits. So n is 4. And I have 2 checks, which are clearly linearly independent. So how many qubits, how many qubits can I encode in this space, this +1 eigenspace? 2. You're not allowed to say anything. So encode, am I writing large enough? 2 qubits. No. Okay. Okay, I won't write then. Okay, so so we'll talk more about this code as a good simple example. One thing about non-stabilizer codes, I will not talk at all about it because I'm also not the expert on that area, I have to say. But you can define classes of non-stabilizer codes, which also have interesting, related to, topological properties. And interesting classes, of course, it's not trivial to define this subspace. It has to be a common eigenspace of some bunch of operators. And if these operators commute, then it's, at least we know there exists some eigenspace. That's a common eigenspace of all of them. If they're not commuting, then it may be hard to find such a space. Yeah.
Can you multiply these 2 elements in the group?
Yes, yes. That y, yes.
It's not an independent check?
That's not an independent check because it's the product of these 2. Yeah, so if I take products of them, I get a dependent check operator. Right? Because the eigenvalues, if I know the eigenvalues of these, the eigenvalues of that check is fixed. Right? So I cannot independently choose it. Okay, so for the non-stabilizer codes, there are classes of codes. They're related to so-called Levin-Wen models. And the checks still commute, but they're not Paulis. So you don't have that nice structure where, operators either commute or anti-commute, or the eigenvalues are +1 or -1. Okay, and like I said, there are also generalizations to Qubit and oscillators, and we'll come to that in the second lecture.
Excuse me?
Yeah.
Is there any reason why you only chose an even number of qubits so far?
No. No, absolutely not. No, I can, I can also look, of course, classical codes, they are a part of this, yeah? So I can look at the 3-bit repetition code. So the checks there are, so the code words. That's the repetition code, and the checks are Z1, Z2, and Z3. But this is but we'll come to, this is a classical code. I could look at the classical, I could use it as a quantum code. I'll show you actually an experiment where they've realized this code. But it's not very interesting as a quantum code, or has limited interest, I would say. I'll come to that. Other questions? Oh, yeah.
There's something about the non-abelian subspaces, codes defined by non-abelian subspaces, subgroups. Sorry.
Yes, there are also codes that we go beyond. I mean, this is not a necessity that these checks all still commute. There are also codes of that kind, indeed. I mean, they're what to call, in general, they're non-additive codes. There are different ways of viewing the stabilizer formalism as additive codes over a certain field, and then there are non-additive codes. Yeah, but
I want to know what is important that
well,
part is important that
it's important that it gives you a lot of simplicity, and it allows for fairly easy constructions of these codes. It's this is just general. This is just true for these qubit stabilizer codes. Yeah, yeah. Thanks for the question. Yeah.
How can they be consistently enforced?
Yeah, not in general. Yes. Yeah. Yeah. Okay, so let's move on to the. Yeah. Okay, so now, so if we have if we did look at the checks, we know how many qubits we encode, and so we could say, where did I put the marker? We could say, okay, for this code, I could find states which I could call these, encode 2 qubits, so I could find these vectors. But I'm never going to write down these vectors. For 4 qubits, it's still not so hard. It's actually very simple here, but I don't want to write these vectors. I just want to define the operators that map these vectors onto each other. So there should be some logical x1, and there should be a logical x2. So that's on the first qubit, and that's on the second qubit, and there should be some logical z1 and some logical z2. Right? And the properties of these things should be, of course, that these anti-commute and these anti-commute, what am I saying? These anti-commute, and these mutually commute, this one and that one, right? Because they act on different qubits. Okay, so yeah, so there should be some logical operators if I encode n minus k qubits. And so how do we find these? Well, again, it's very simple. There are members somewhere in this Pauli group. Let's find them. So they have the following property that if, for example, I take a logical x and I apply it to 0, that is defined as giving me a logical 1. And so if I apply an element in S on that, I get this. And of course, this I know should be 1. Which is x is 0. So it means that this logical x should map a code word onto something else that is stabilized in here. Now, if S and X, they either commute or anti-commute. So if they commute, then I'm fine. Then I can satisfy this relation. Notice that if they anti-commute, I cannot satisfy this relation. because I get a minus sign. Yeah? So we need the logical operators to commute with all the check operators. But of course, they cannot be in this group S. Right? They cannot be in this group S. Why not? Because the elements in the group S have trivial action on the code space. Yeah? So they are in the centralizer of S in P. What is that structure? It's basically the centralizer, just the definition, the centralizer of S in P are all the elements in P that commute with all the elements in S. And the fact that there exist such elements is sort of guaranteed by our dimensional estimate. So if the code space is one-dimensional, of course, then S coincides with C of S. Okay, so we can write the centralizer of S. That includes, it's everything in P that commutes with everything in S. That includes S itself. And then it has these logical operators. Now, one thing to note, and this is an important point, is that the logical operators are not unique. Why? Because I can easily multiply a logical operator by an element in the stabilizer group, and it will become the same logical operator because that element in the stabilizer group has trivial action. Yeah? Okay, so that's the basic code structure. So you could define the, for example, for this code, we could look at what the logical operators are. Of course, we're free to call one qubit, we are very free to choose these things. Right? So this is then, say, Z1. This has to anti-commute. So Z1, Z4. Right? So these anti-commute. So now I should choose some Z2 that is, I'm just sort of see if I can construct this. So this is, well, let me check this. Z1, Z3. Z2 has to commute with X1. And Z1, Z3 commutes with X1 because it anti-commutes twice. And then I need to choose one more element. So X1, X4. So these anti-commute. And these anti-commute. And these commute. I think I did this well. But like I said, these are not unique. I can multiply these elements with elements here. So for example, this is X1, X4, but I multiply it by this. And then this is equivalent to X2, X3. Okay? Okay, so these are just some basic examples. Okay, so now, what about errors? So some general comments. So quantum error correction was developed because it was quickly foreseen that if we imagine using very basic quantum degrees of freedom, like an electron spin, or the polarization state of a photon, or a superconducting qubit that you've heard about, that these are very fragile components because they're very small. There's no redundancy in them. One single electron spin, and so they lose their state within, well, here say less than 1 millisecond. For superconducting qubits is 100 microseconds. So, and there are fairly involved noise models, or not so involved, that describe what happens with these qubits typically. So typically, and this is very general, but it's not pertains to all qubits, I define my qubit as some two levels, a 0 and a 1, which are different in energy. That's useful if I want to do some rotations in this space. But it's not so useful because if I couple this to a heat bath, then it equilibrates at some, after some time, and one is, probably more likely to be in the 0 than in the 1, right? Because of energy relaxation. But on a shorter time scale, one expects that these qubits dephase. Yeah? So the dephasing, so there is these two energy levels, but what defines these two energy levels defined by the Hamiltonian, which is not an isolated system, but is sensitive to properties of the environment, charges, fields, and so on, which fluctuate on some time scales. Yeah? So that leads to dephasing, and then energy relaxation, so leads also to decoherence. And we can model, I'm not going to go into how you model these. You can model them with more detail in terms of, master equations and so on. But for the purpose of error correction, we can, it sort of suffices, or to some extent suffices, to say that these induce Z errors and Z and X errors. And I'll come to this discretization of errors in a moment more. Of course, all gates and measurement are also realized approximately. So the question that came up very early in this area is how we make a computer out of these faulty components. This is a question that von Neumann asked in the 50s when we didn't have very reliable classical computers. And it asked about the theory of fault tolerance. And so the idea is that instead of encoding our precious information in a single electron spin, we'd like to encode it in 100 electron spins. So if every electron spin represents a qubit, it's 100 qubits, and we'd like to keep the state of those qubits in some two-dimensional subspace, encoding one logical qubit. Now, I have not said at all about what the properties of this code space are. I've talked a bit about logical operators, but of course, I could choose codes that are very useless. And so one has to choose, one chooses the codes that are physically interest relate to the error model that we have, right? To what we believe are the physical mechanisms that destroy the information in these qubits. Now, one of the simple models that we use in the theory of quantum error correction is that the noise or decoherence is independent and uncorrelated for every elementary qubit or component. Let me say that a little bit more clearly. So if I have n qubits, a very simple noise model is to say is that everyone in a certain period of time undergoes undergoes an X, Y, or Z error with some probability. Yeah? And if I now go one step further, I can say, well, I'm also doing some interactions. There are interactions that go on between these qubits. So there's a C0 gate happening. Then I say, well, that C0 gate will succeed with some probability P, and with probability 1 minus P, it will fail, and it will, there will be an additional X, Y, or Z error added. At this moment in my lectures, I don't really care about the details of this. This comes to the thing that this field is very well developed, and there are people in the audience who've also done work on this. There are more general noise models, and there are extensive discussions also on the proper noise models to use at the theoretical level. Yeah? So there are noise models that assume correlations in time and correlations in space between the qubits. So if this qubit undergoes an error, it's also likely that that qubit undergoes an error because they see the same environment, the same physical environment. But for now, in order to discuss the basic quantum error correction, I will not use or think about these models. Okay, so we will, in order to understand how to choose your code space and understand what protection you get, we assume that the only errors that occur are Pauli errors. So there's no gate happening yet, And the elementary qubits, the n qubits, just undergo bit flip, phase flip, so that's how we call these, or both, y error, which is the product of the two, these errors. Now, why is that sufficient? This is an early observation in quantum error correction. You can also find this in the book of Nielsen and Chuang, is that one way of looking at it is that any operator on a single qubit can be expanded in terms of a linear combination of x, y's, and z's. It's an operator basis. That's one way of looking at it. One can also, differently from that, you can see this in a few slides, where if we detect what measurements, what errors happened, we actually wish or want to do a projection where we project the sort of continuum of possible errors onto a discrete set of errors. So, because you could say, well, this is not really a fair representation of what happens physically, because I may just have some sort of jittering levels here. Or I have maybe a gate which does a rotation and I slightly over-rotate just by some angle delta very small. That's not this discrete error. But the way we treat these errors, at least in theory, is that we project onto these possible errors, and the probability with which we see that these errors happen depend on how far we over-rotate it. Okay, but we'll come to that in a moment. So one notation or formulation, so what I call the weight of a multi-qubit Pauli error, so it's a product of Pauli, just to note it like that. It's the number of qubits on which it acts non-trivially. So the weight of x1z3 is 2. So now let's imagine, I just want to give you a heuristic argument, what happens when we choose our code space widely. So as an error model, which is slightly more general as the one that I said before, let's imagine I have an error model which has the following property. The probability for an error E scales like a constant times some P, which is less, between 0 and 1, and then to the power the weight of E. So it means that high weight errors are much less likely than low weight errors. And this goes very fast. And this decay is very fast. But we could have other decay functions, and then it may be more problematic to actually obtain full tolerance results. But okay, so let's make that assumption. Then what we want to do is we choose our code space. So it's that subspace of n qubits. We want to choose it such that the low weight errors, which have weight, say, less than some t, they should be either harmless, trivial, meaning they should be maybe elements of the stabilizer, or that they can be corrected and detected. That's what we want to choose. And I'll show you in a second how we choose that. Let's assume we can do that. That we can choose our code space such that these low weight errors have that property. Then it's clear that if we encode our data in this code space, and we do perform error detection and correction, that the only bad errors that we're left with are the high weight errors. So the probability for a logical error on our new encoded qubit should scale as something which goes like p to the t plus 1, because there are only contributions from these high weight errors. And there is some constant which I show depends on n, because of course I have an n qubit state, and there's, I say, well, I have to put t plus 1 errors anywhere, so there's n choose t plus 1 places to do this. So there is some prefactor that depends on n. I don't get everything for free. I do pay because, in some sense, I increase the error rate if I have more data around, more places where errors can occur.
Probability. Can you specify what probability you are talking about? C times E over E. What to detect the probability?
Sorry, the probability. So the probability for logic. So I have encoded now Let me just the marker. So I have, let's imagine I have prepared a logical 0, yeah? And that is an n-qubit state. And I have some probability that errors happen, yeah? And then I have a step in which I correct or detect and correct any low-weight errors, yeah? So the only errors that can lead, so what is I can bound the probability. So what is a logical error? A logical error would be a process by which this gets taken to 1. Yeah? Or it gets taken to alpha 0 plus beta 1. Which cannot happen really with Pauli errors.
Probability means
The
0 to 1. The probability to be
I'm just saying that the chance that there is a logical error is now very much suppressed. And it's suppressed depending on this t. And it depends on some prefactor. Because the only errors that actually will affect my logical information are errors that are weight t plus 1 or more. That's where all the bad stuff. I'm not saying that an error of weight t plus 1 will do this process, but I say that at least the errors which are weight of less than t, they are harmless, because I can detect or correct them. Is that, yeah, okay, maybe it becomes more concrete. Yeah.
Why do we need C for the
Oh, I mean, I'm just writing. The C is harmless. Yeah? So the idea is that the essential thing is that there is this decay behavior. So there is some constant. Yeah? So the point is that would like to say, well, okay, what's the most general error model under which my codes will do well? I can put a C here, so let's put it there. Yeah?
Which one about the weight? You mean in expectation, right?
No, it's the weight is just this is an operator. These Paulis are operators, and on the qubit 2, it's the identity operator.
Yes, but
And the weight is just the number of places where it's not the identity.
But if you look at it as the basis of if the Paulis is the basis of the possible operators, then it's likely that you will have operators which, with low probability, act on any qubit. No? Like, in reality, I would just assume it makes sense that, in general...
No, I mean, okay, so let me just say one. Okay, so the thing is that if I have n qubits and each of one undergoes a x error with some probability, yeah. So with probability p, I have an x error, and with probability 1 minus p, I have no error, yeah, identity. Yeah. Now, clearly, the probability for 3x errors is p to the third, then, yeah, and 3x errors is x1, x2, x3. Yeah? So that has weight 3. And so, is this answer your question, or I don't know?
Yes, modify.
Yeah? Okay, so that's the very simple error model in which I say every qubit undergoes error with some probability, and then it's clear that you get, such behavior. Huh? But this behavior can be observed also if there are possible correlations between the errors, depending on how strong these correlations are. But I don't want to go too deeply. I just want to sketch you sort of the basic idea of you have to argue that using a code, instead of representing your information in one spin, you do it in 100 spins, that there's a payoff, right? If there's no payoff, it's a pain. Yeah? So but the payoff is that the logical error rate should be suppressed like this, and that this t is a crucial number, is the number of errors that you can correct. And so what you do is you compare that logical error rate with the basic error rate. So if you just had one qubit with this error model, it had a probability CP. Now you had to do more stuff, which I'm, yeah?
You detect the error.
I will come to all these things, yeah. So the idea is that you would compare this number c times p with the c prime p to the c plus 1, And then with that, you say, okay, equate them, and that's the P. If my error rate is below that, my quantum error correction helps. And I'm putting this in a very sketchy form. I'll come to that a little bit more rigorously, because all the things that you use here, you know, they're not necessarily perfect either. Here I have to say I can detect and correct the error. I have to do that too. Okay. So now let's talk about errors. So I had the structure, I erased it, but it's not here. So I have I had the stabilizer S, and then I had the centralizer, everything that commutes with S, and we're only looking at Pauli errors, so that's basically the rest of what's in this Pauli group. Yeah? Now, so an error E is just some element in a Pauli group, and of course it either commutes with all elements in S, in which case it's in control, then it is in the centralizer in S. Then E is either trivial, yeah, that's okay, or it's a logical operator, which would be bad. Yeah. Right? That would be an error that just implements a logical operator that is not what we want. Second possibility is that this error is such that it anti-commutes with a few elements in S. Yeah. So if we have a code word, the error happens, we measure the eigenvalue of that element in S, we will find a -1 eigenvalue, whereas before it was a +1 eigenvalue. So that means we can detect the error. So that's the idea. You asked about detection. Yeah. In order to detect and then possibly correct the error, we measure the eigenvalues of the stabilizer. We measure the eigenvalues of the generators of the stabilizer group. Now, the distance of a code, like this Qubit code, is defined as follows. It's the minimum weight of a logical error. This should not be a logical operator. And like I said, it's not the logical operators are not unique. First of all, there are at least 2 of them. So I have to look at what is the one with minimum weight, and they're also not unique. So maybe when applying elements of the stabilizer to it, I get an operator which has lower weight. Now, for example, you can look at this simple example. So I wrote down the logical operators here, and you can see that these are all weight 2, and if I multiply them with elements in this stabilizer, they're still weight 2. So the distance of this code is 2. Now, so from this observation, it immediately follows that the code can detect all errors of weight less than D. Because all these errors will never be a logical operator, and they're either trivial, they're just elements in the stabilizer group, or they anti-commute with some element in S, and therefore, by measuring the eigenvalues of S, I can detect them.
So, what
yeah.
does it mean that error is trivial?
Trivial just means an element in S. It's a stabilizer check. So a trivial error, in this case, is the error that flips all the bits of the, all the qubits. There's an error.
What is P bar?
Sorry?
What is P bar?
P bar. So if I have a bar, it's a logical operator. So before I had X bar and Z bar, yeah. And now, so P bar is a logical operator, yeah. So I define. So let me see. So remember, I had this Pauli group. I had elements S, and I had things in C of S. And C of S is a group which includes all elements in S and includes the logical operator. So P bar can be X1 or Z1, etc. These are the logical operators of the encoded qubits. Yes? Okay, so now I want to look now at the more interesting code, so the smallest code. So okay, so first some notation. So the way we denote the stabilizer codes is as follows. So one of the first codes was Shor's 913 code. It's a code that encodes 1 qubit into 9, and the distance is 3. Yeah? So the logical operator has weight 3 and not less. And the smallest code, which encodes 1 qubit into something and has weight 3, is the 5 qubit code. This is a code. I should keep that marker there. Okay, so in that notation, this is a code that encodes 2 qubits into 4, and it has distance 2. Okay. Okay, so now I am not going to... okay, so you have to ignore this figure because it's not optimal, and I'm going to draw a new figure. I know this whole thing. So I think I'm done with that code. Okay, so the Shor, the 9 qubit code is actually can be viewed as an example of a family of code which are called Bacon-Shor codes. Which encode, and there's a slight, oh, maybe you come to that later because they're actually subsystem codes. They encode 1 qubit into n squared and have a distance n. But in our case, we're taking n as 3. And, this blue thing I shouldn't have used. That's why it's on the phone. Okay, so the... and so I have my 9 qubits. And so what are the generators of S? Well, they are the horizontal ZZs. I just load them as this line. Huh? So this or that. Those are, all these Z's are generators of S. Do you understand what I mean? So every pair of Z's like this. And in addition, I have some double row operators, 1 and 2. Let me note some. I think I have this. This is a qubit. Yeah. And the double row operators are these. So it's x's on those 2 lines, and the other one is x's there. Yeah?
Excuse me.
Yeah.
Now you're just considering one type of error, just bit flip or defacing, or just one of those.
Right now, I'm only considering Pauli errors, which means x, y, or z,
Okay.
and products thereof. Yes. And I will show you in a moment why this is warranted. Yeah. Okay. So we can do our little exercise and say, well, okay, so how many? So I have 9 qubits, and I have how many checks? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 independent checks, so I encode 1 qubit indeed. And for that 1 qubit, I now need to find the logical operators. And like the logical operators have to commute with all the checks, but they should not be generated by the checks. Okay, so let's see what we can do. So I claim the logical x is x1, x2, x3. So that's x, x, x. Yeah. That's one choice, right? Because I could multiply it with this double row operator, and it becomes then x4, x5, x6 is an equivalent operator. And the logical z, I can take to be z1, z4, z7. And again, I could multiply it with operators, and its weight will not go down. So that's why the distance of this code is 3. Yeah. So now what we do when errors happen. So how do we, now I'm not saying to you how you actually measure these stabilizer checks. I'll do that in the next slide. But I want to say what you do with this error. So let's imagine I have an error happening Z1. Yeah? Here on this qubit. And I will measure the stabilizer checks. And remember, if they anti-commute with the error, then their eigenvalue will be -1. And otherwise, they will be +1. Yeah? So the Z1, of course, only anti-commutes with the X stabilizers. So, and it anti-commutes with this double row operator. That's this one. And it commutes with that one, clearly. Yeah? So, what we do is we, on the basis of these eigenvalues, we make an inference about the error. We pick an error, E-guess. Let's assume it's Z2. And then we can make a statement about whether we did well or did not well. Now, there are two possibilities. One is, let's say we take E-guess to be Z2. E-real times E-guess is an element in the stabilizer. So actually, maybe I should say this. So the properties that E-real and E-guess have is that they both have the same syndrome, right? And that implies that the product of them will commute with S, with all elements in S. Okay? So E-real times E-guess, which is the real physical process that happened, is an element in this centralizer of S. So it's either in S, which is good, because I basically corrected the error modulo an element in the stabilizer, or E-real times E-guess is a logical operator. Yeah. Let's imagine, so in this case where I take E-guess to be Z2, you notice that Z1 times Z2 is one of these, and so it's an element in S. In the other case, let's imagine I do something a little stupid. I infer that the error is Z4, Z7, may not be very logical, and then that is actually a logical operator, as Z4, because then I have done Z1, Z4, Z7, and that's a logical operator. This procedure of taking the error syndrome, which are the eigenvalues of the stabilizer check, and inferring what error is most likely to occur, is what's called decoding of the error syndrome. Now I want to give you an argument why a code with distance d, which is equal to some 2t plus 1, can correct t errors. It's a very simple argument, and it relies on the fact that we can do something called minimum weight decoding. So what is minimum weight decoding? We are given these eigenvalues of these checks, and we just say, I'm going to infer, we're going to guess the error that has minimum weight that could have led to this syndrome. Yeah?
Is there no third option?
Yeah, there's no third option because of these things anti-commute. So E-guess and E-real had the same syndrome, meaning they correspond to the same eigenvalues of the parity checks, meaning they had the same commuting anti-commuting structure. So if this guy anti-commuted, this guy would also anti-commute. So the product of them will commute. And the product of them will commute with all elements in S, so therefore it's an element in the C of S. Okay, so the minimum weight decoding is essentially choosing an E-guess with minimum weight, right? Like this choice, for example. Okay, so now clearly, so like I just argued, when can error correction fail? It's in the case where we infer an error such that the guessed error times the real error is illogical, right? Because we inadvertently did that logical then. The noise did E-real, and we did E-guess, and together we did logical operator, and we were not aware of that. So that's the thing that we have to argue cannot happen. Okay, so what minimum weight decoding? Well, it's very simple. So let's imagine. So I want to show this statement. So the code can, with that distance, can correct t errors. So we imagine that errors that only errors happen that have weight t or less. Yeah. That's so E real has weight t or t or less. Yeah. And then E guess times E real. E guess I choose as the minimum weight error. Now, of course, there is a minimum weight error, namely E real, that has weight t. And if I multiply these, then the weight is at most 2t. Right? And 2t is less than the distance. Therefore, and the distance, and therefore this cannot be a logical operator. Cannot be some p, right? Because the minimum weight of a logical operator is 2t plus 1. Very simple. Now, one more comment I want to make about the distance. Yeah. Okay, so the distance of the code is really the important feature of the code that describes how good it is in correcting low weight errors. And our noise model is such that we assume that low weight errors are the dominant errors because they have the lowest probability. Yeah? So that's how it ties together. One thing I want to say about another way of looking at distance is that, well, first of all, you can detect errors with this of weight less than the distance. But there's another way, and maybe this connects to some later lectures that you'll hear, is that if you know, so there's another, okay, so let me see, it's a bit of a side issue, but I like to discuss it. Let's imagine I have a code word, psi, and I have a different situation in which it's not, I have some bits that flip or some phase errors that happen, but some part of this code word falls into a black hole. Yeah? And so d minus 1 qubits fall into a black hole. What does it mean? Of course, this is only, what does it mean? The qubits there are lost. Huh? And I may as well ignore these qubits and replace those qubits by the completely mixed state. Yeah? So what happens is that now I have a state rho, tensor, identity on 2 to the n. Yeah? So I could replace these qubits by some completely mixed state. You can also, I can talk about this as falling in a black hole. I can also call this an erasure error. So the state of d minus 1 qubits get erased. So I could do a depolarizing error channel such that these qubits completely lose their information. I can represent them as the completely mixed state. Yeah? And the essential point of this noise model is that I know which qubit underwent the error. Yeah? So, which means I can say that basically the real errors that happened only were taking place on these d minus 1 qubits. Yeah? So if I now want to infer, so now what I do the same thing there. I measure the parity checks, I determine, on this state, I have obtained this state, measure parity checks, and determine their eigenvalues. And then I do some inference, what error took place. And now, of course, it's clear that I'm going to guess errors that only act on on those d minus 1 qubits, right? So it's also clear that E real times E guess, because they act on the same d minus 1 qubits, that the weight of that is less or equal to d minus 1. And therefore, that thing cannot be illogical. Therefore, E real times E guess cannot be a logical operator, and therefore it must be trivial, and therefore I correct my error. Yeah? And yeah?
In this case, the error model is not a Pauli operator.
It is actually. Well, it's a Pauli. I can write the identity as something where I get I have the original state, and I apply with equal probability, x, y, and z's with I don't know what probability quarter or something like that, and then I map. I can write any. I can write the identity as any state in which I apply x, y, and z errors with the right probabilities with high error rate.
So I was wondering whether the measurement of the parity check actually applies on other flip.
Well, what the measurement of the parity checks does is, so what here happens is that they all get depolarized, but if I measure these parity checks, I project on certain errors. So, with some probability, I say, oh, x errors happens or y errors happens, yeah?
I see.
And then I correct those Pauli errors, yeah? Yeah.
If there are Pauli operators, then why do you need them to know which qubit they operate on? Because if you know what qubit they operate on,
I didn't know what Pauli errors. I don't know. Those qubits. Well, first of all, I could say the state is lost, and then it's clear. I need to, if I want to retrieve the state, I need to do something, right? It's not automatic that I can retrieve. So what I want is I want to map this onto the original encoded state. That's what I want to do. Can I do this? Yeah.
but if you know exactly what the state is, and you encode some amplitudes A and B, and they don't get affected, and you still have one qubit with this A and B, and you know which qubit it is.
Yeah, but of course, yeah, but you encode the information, the logical information is very much spread out over the n qubits. And I lose d minus one of them. And the fact is that if the code distance is d, then that's okay. I can retrieve that state of those qubits. And that's captured by the distance.
So I just want to be clear.
Yeah.
What are the generators in your S here? Looks like you have 8 of them. Do you have 6 horizontal?
S there.
Yeah.
The generators are these, there are 6 of those. And then 2 of those, so it's 8. And there are 9 in total qubits. So I get 1 encoded qubit. I have 8 linearly independent checks.
Okay.
Yeah?
And so that those pictures down.
Yeah, ignore. Sorry, this is.
Is that an equivalent?
Well, okay, so there is a. So maybe I'll come to this. The Bacon-Shor codes, they are subsystem codes in which you actually define not an abelian subgroup, but a non-abelian subgroup, and in which you break down these operators, these double columns. I can break them down as little vertical lines. So I have a generator of a non-abelian group, which are the horizontal z's and the vertical x's. And then you actually measure those, and you combine information of those. And there, this is a non-abelian group, and it has a center where everything commutes, and that is this S. And not quite, but I combine the information those to determine the elements in this abelian subgroup that's in there, and that's how I do error correction. But maybe let me see if I get to that. Okay, so that's the connection with black holes. Okay, so how am I doing on time? Actually, I've
20, 25 minutes.
okay. Sorry. Okay, so how we measure the parity checks? Yeah, so I have these check operators, and it's important that I want to measure, say, Z1, Z2, without actually measuring Z1 or Z2. And this is not very simple. I mean, I can write a circuit how you do it, but in practice it's actually not simple, I think. But okay, so we start with how we do it in theory. And in theory, we run this type of circuit. And P here is some Pauli, some product of Paulis. And this is a controlled Pauli. What it means is that if this qubit is 1, I apply P on this input. Qubit is 0, I don't apply P. No? And so we prepare this qubit into the plus state, 0 plus 1. And we measure it also in the plus minus 1 basis. No? And now you could verify for yourself. I think that's not so hard. That what happens. Okay, so let's look at what happens when the input here is a +1 eigenstate of P. Well, nothing happens then, right? Because I have a +1 eigenstate here. Whether or not this qubit is 0 or 1, I apply P, but P doesn't do anything. So here I have a plus. So I'll measure a plus always, right? It's also clear what happens if this P, if it's a state which has -1 eigenvalue with respect to P. Why? Well, I start here with 0 plus 1. The 0 state, nothing happens. But if I have the 1 state, I pick up a minus sign here from applying P. And that minus sign I can just include here. So plus goes to minus. And if I measure it, I find a minus state. But if so, by linearity, if I put in a linear combination of these things, and I do here a projective measurement, projecting onto plus or minus, I end up, if I find plus, I end up with a +1 eigenstate of the operator P. So if I do this for all the parity checks, and I always find a +1 eigenstate, I have a word in the code space. So if a very tiny error occurred, let's imagine I can do this circuit. And here this input is just slightly rotated out of this code space by some angle delta. And I do this circuit perfectly, then most likely it just be projected back in. And so no error occurs. But with some very tiny probability, I project it outside the code space. And then what error happened? Well, what I have here is a state which has -1 or +1 eigenvalues with respect to the parity checks. And those states I can only get from applying Pauli errors on a state. So that's why, in other words, the Pauli error model, if I can do these measurements, you don't need to go beyond that in this formalism. Okay, so there's a discretization of a continuum of errors onto Pauli errors in this fashion, assuming we can do this. Now, one thing, if I have a gate like that, and let's say this is, the P is 4 x's, x1, x2, x3, x4, then the circuit looks like this, with these knots. So now I think the real issue about realization of quantum error correction is whether we can do and how we can do fast, high fidelity parity check measurements in the experiments. And not pick up any information that is not parity. So we have to, because typically if you'd have 4 of these qubits here, and they each have, they're each represented by some degree of freedom, which is 0 is the low energy state and then 1 is the high energy state. It's much more natural to pick up a different signal from the all 1 state than from the all 0 state. Why? Because it's different energy. But in this thing, we want the all 1 state to have the same response as the all 0 state. Now, in principle, one can do that with this circuit. But this circuit, of course, is also, it requires 4 CNOTs, requires an oscilla. It's also going to be noisy. So we have to deal with that. Okay, so now, yeah.
With this code, you're robust against all Pauli errors. But imagine that you have a system in which, for instance, big errors can be neglected because the energy difference.
Okay, yes, yeah, more
like this,
Z error, yes.
Can you design any?
Yeah. So you have.
That information is more efficient or whatever.
Right, because I said the distance, but you can have. You can say the code, the distance in my definition was the distance of any logical operator, x or z. And so you could say, well, I want a code that can correct, k x errors and k prime z errors. Yeah, you can do that. Yeah, but the thing is, you have to be careful if you do that. That also, if you do logic like you do a Hadamard gate, well, then your x error gets mapped onto your z error, and so. Yeah, but there is work on that. Actually, John Preskill also worked on this. Yeah. Okay. Now, so measurement is actually highly non-trivial. Now I want to, so I think, let me see whether, I want to finish with making a few comments which pertain a little bit to why, doing this prescription of, okay, so I haven't talked about how you encode a code word, or how you prepare these states, but why the procedure of doing these repeated parity checks is not so simple, and also discuss some ideas that actually if people have suggested how to do this and criticize this a little bit. And maybe you're not familiar with this idea, so maybe this is not so interesting. But okay, so first of all, measurement is not like this naive picture with, projection into, plus or minus. Yeah. So in experiments like the superconducting qubits, I'll show you in the second lecture, it more looks like something like there's a voltage and it sort of jitters. And it's sometimes very noisy, and then you have to kind of put a filter on it and interpret this data record. Yeah? That's where you say, well, there are quantum jumps. You say, well, for example, I start with doing, as I mentioned, do a parity measurement. We'll see in the second lecture some kind of parity measurement. And it starts with something that looks like a 1, and all of a sudden it jumps to a -1, and it goes to 1, and I have to interpret this as the error syndrome. Yeah? So how reliable is this? Now, one thing that that also has so one thing that people have thought was attractive is that to kind of use this model, you say, okay, I do my logical gates, perhaps, the C naughts, and then I do my measurement. It goes to the outside world. I outside the fridge, back, outside the low temperature area, amplified, and I do some classical processing, infer an error, and that I use to send the pulse down to the experiment to do the correction. Yeah? But there is interest to do this more in a self-contained manner, at the place where the qubit lives, so to say. So some people have called this, which is Peter Zoller and so on, they've called it stabilizer pumping. So in this kind of model where you say you want to actually correct the error without an explicit measurement. Yeah? So it's more like you set up, so the idea is, for example, you set up some process which you can model by a Lindblad master equation. And so if it's a closed, so your rho is maybe your encoded state, and there's some natural Hamiltonian, and then you've engineered your environment such that there's also it's an open system, and it's such that, and such, Lindblad master equation looks like this. And such a quantum, you've engineered it such that these LJs are something like this. That let's imagine that I have a code which has these check operators Sj. So there are many of them, and one of them is Sj. Let's say for this code I discussed, there were 2, XXX and ZZZ. And I want to do something where if this has -1 eigenvalue, I do a correction step. So this correct J is some bit flip I do somewhere. Yeah? So this was proposed by Zoller and all, and they do experiments in the ion traps. They try to do this for Bell states, and then I'm not sure they've done it for this XXX and ZZZ already. And so it would be nice if you can do a correction. You say I measure the parity check, and then immediately I do a correction. Yeah? And this may be a possible route for small codes, but I like to make the point for the codes that we are interested in, for topological protection, for good protection, other reasons to be interested in those codes, that they would require, if you want to have some kind of they require some non-local or classical logic. And I want to illustrate that in the following manner. So this is a way of saying, well, immediately feedback, and I just set up a process. This Lindblad equation is such that it drives the system to the code space. So every time an error occurs, there's a process that detects the error, does a correction, and then Scylla, which is used, or is set back to 0. So we have some process like, we have a plus, we have this thing, and then depending on the state of that plus, we do a correction. There's a reset, which is a dissipation. It equilibrates down to 0, and then it goes over again. Yeah. Now, this is a very simple thing, and I will just show why this is wrong. I mean, it's very simplistic. In this way, for example, for the 9-qubit code. For example, you say, let's imagine, so the problem with this correction is that you only use information of what one stabilizer check. You're not comparing what this stabilizer check guesses outcome or this stabilizer check. Yeah? So, for example, you could say, well, in this making sure this slide. Which one is my? Sorry, I'm just trying to find back this. Where's my picture? This one. Yeah. Okay, so here I have, say, I measure Z1, Z2 is -1, and I have to make a decision about what to do correction. Now, I'm also going to measure Z2, Z3, and I want to, of course, to make a correction that is, good. So I'd say I correct X1. Yeah? So that would be okay. Z2, Z3 is -2. I could do P correct is X3. But it's obvious that if I would find a syndrome where I say, this check has -1 eigenvalue and this one, that the most likely error is X2. Yeah? Obvious. So I need to combine the information on these two checks to find the most likely error. Very simple. Yeah? So, but now I want to extend this. So I can generalize this code, not having 9 qubits, but something larger. And let's imagine I measure the checks on this line. Yeah? And then you can maybe understand what happens. So what you actually get, maybe I say this in the next slide. Yeah. So I take the checks on this horizontal line, and these -1 checks, I put them in the middle, and they're like domain walls. Yeah? Why are they like domain walls? Is that if an X error occurs here, then those two checks will be -1. Yeah? So in this way, I could look at this line, and I draw these dots where the syndromes are -1. Yeah? And the errors, the possible errors, are in between. So for example, I find a syndrome that's -1 here and there, then I could say, well, it could be caused by an error here and there. Right? Because if an X error occurs here and there, it actually commutes with this check, so there's no -1 eigenvalue here. It's just at the end of the error strings. And I'm telling you this also because this is, if you understand this surface code error correction is fairly simple to understand. Yeah? So what I do, what I find as my error information is something like a string like this. Now, if I were to do some local error correction, so what if I were to find at these positions, I find a -1 eigenvalue. At the other position, I find +1. Now, what is the error that would be most likely if I do minimum weight decoding? I say, well, okay, errors here, errors there, errors there. Yeah? That minimizes the weight, because another pattern where I just use, where I would do this, for example, and I have to match this, well, let's say this ends here. This has periodic boundary condition there. That would be higher weight. Yeah? But it's clear that you'd have to combine information about at least neighboring parity checks, or further along, you have parity checks on this whole line to determine what the minimum weight error is. Yeah? So the problem is that there is a certain, in order to do the correction, if you want to do it with some logic, with your basic qubits, that logic is not completely trivial, and it's not completely local. Because I could do something where I say, well, I check my neighbors where there are also, I'm faulty, I check, I have -1, I check my neighbors, and then if my neighbor is -1, I match it there. Yeah? But if it doesn't happen, I need to go to look at the neighbors of my neighbors and do that. Yeah? And in that way, the error correction, and we'll see that for the surface code, is the non-local processing, at least for stabilizer codes in low dimensions. And I could say more about this, but that is, if we say maybe the easiest way to realize error correction in the lab is by engineering the correction step as part of the quantum circuit, then we do have to really realize some logic, and that all has to be done fault tolerantly. Okay, so now, as to finish, I want to show you from small experiment, not go in all detail, because I'm not showing you what this actually is as a device, just as a circuit. So in superconducting qubits and also in Eintrap qubits, people are starting to be interested in realizing some error correction. So in 2012 there was this work, and I just want to show you what actually is done, and maybe also show how far this is from anything that we want to do. So what can start by, so what they do here is realize the 3-qubit bit flip code. So the 3-qubit bit flip code has these two checks. It's a classical code. It's just a repetition code. The code words are 0, 0, 0 and 1, 1, 1. And the logical operators are logical x is x1 to x2, x3, and this is the logical z. And the reason that it's not a good quantum code is that the logical z is a single z. So if I have a single z error, I map a logical plus onto a logical minus. So what happens here in this circuit, which you may not be able to see, is that there is an encode. So there's a state psi, and these are ancilla qubits set to 0. And this circuit does basically 2 C0s that map this psi onto the logical psi. And so I have 0 psi 0. And so if I do a circuit like this, then this is the logical psi. If I'm using these code words, right? Because if I write this alpha 0 plus beta 1, I have this becomes alpha 0, 0, 0 plus beta 1, 1, 1. Yeah? And then they have some single bit flip error, which they actually purposefully do. They actually do some rotation. And then they don't use an ancilla to the error, because they just decode. Yeah? And then they need to do some correction. So the decoding is just the inverse of this circuit. And then the thing is that the information under decoding, the information about the parity checks presides in these ancilla. Yeah? So if no error happens and I do the circuit, the ancillas are back to 0. And you can check that if if an error happened here or an error happened there, an error happened there, the ancillas will be set to 3 different states.
Is there any possibility to destroy the original code by taking the error process?
Well, the idea, that's why you use an ancilla. So you say, I don't want to, I have encoded my qubits. In the previous slide, let's say I have 4 qubits encoded, and I don't want to directly measure them, measure them in the z basis. I want to couple them to an ancilla qubit, which I measure. But of course, I try to avoid destroying this code word and introducing more errors by doing this parity check measurement. That is the goal, of course. But it inevitably leads, actually there are people that think about parity check measurements in superconducting qubits, and you see that it eventually, it also can lead to additional dephasing, which is not obvious that it should lead to some additional decoherence on the code words also. But if this is limited, then that's okay.
Also, this error also evolving with respect to time. So
what they are
evolving.
Evolving?
Yeah, the code is evolving
in this model, I only do, like, I do a circuit where I say I do this gate, that gate, and nothing is evolving in between. But that's a model. For the experiments, you always work in the rotating frame. So, you know, the qubit is always, because it, you know, it has a 0, 1, it's also its own Hamiltonian, but you always go to the rotating frame to cancel that evolution. But yeah, maybe you can. Okay, so so the thing is that the correction step requires that's some Toffoli gate. So there you see that in order to actually do the correction, you need just not like have the answer of one bit of information, but you need to look at both bits to correct the error. Yeah? So this is only a 3-qubit code, but you see you need a Toffoli gate, or you need to compose it into, you know, 2 gates. Right? So in that thing they have a fidelity of 78%, and so these are some data where I say that this is state fidelity. If you have uncorrected errors on the second qubit, by the gates they do, there would be some oscillation. And the goal is that if there's Q errors on the first qubit, second qubit, or third qubit, that this is now at 1. Yeah. But one thing you want you to note is that the logical C is a single C. Well, this code, if you use 3 qubits, you cannot get a code that has weight 2 or more for both logical operators. I don't quite understand your question. So this is the simplest code. It's just a 3-bit repetition code. And there is this logical Z that is the 3, you know, it does Z on all 3 bits. Is that what you're saying? Yeah. But that's equivalent Z, yeah. But if I say the environment may be doing that Z, I have to take the worst case, right? I have to assume that the environment, yeah. Okay. So this is not at all what quantum error correction should or look like in the future. Why not? Well, first of all, we have an encode, which is fine, but we have we're only doing correction after the decoding. So we want to keep the qubits encoded throughout the computation and never do any decoding, because at that point, this qubit is unprotected and we're back at square one. Now, there's the other thing is that here they did the correction as part of the circuit. As part of these ancilla qubits are... this is not some ancilla that you measure and then you get it to the outside world. No, it's all part of the thing. But then you need to do some non-local classical gates in order to process the error if you want to do it in place. Another comment you can make is that there is a concept which we call the Pauli frame, is that we actually, and it's not completely true, but for often we don't actually need to correct the error as long as we know what error happened. Yeah? So let's imagine I know that some X error happened. Now I don't decode, but some Pauli X error happened. Now, so what I have now is the code words with that X on it. That's another code space. It just happens that some stabilizer check is -1 eigenvalue. It has the same distance. It has the same good features. Huh? And if I do gates, we'll come to that. If I do gates that simply propagate this Pauli frame, then so now maybe I shouldn't say this way. Okay, so but I don't actually necessarily need to correct the error as long as I know what it is. Okay, so one can ask whether such a demonstration, although it gets published in Nature, is really demonstrating anything scalable. And I think it's probably a very interesting experiment that was untrivial to do. So it's interesting from just the experimental point of view. But I'm not sure it's convincing as that, showing that we can do some quantum error correction. Okay, so I think I'm at the end of my lecture now.